The other topic for today is phase changes. So this is changing from one state of matter to another. Again, set of notes for you for this in Schoology that you can go ahead and take care of or print and use the ones that are there. All right, so when we talk about state of matter or phase changes, first thing we don't want to do is just give the names of the different ones, right? So a couple things that are going on here. So transitions between solids and liquids. Okay, when I go from solid to liquid, we refer to that in melting as melting in common language. In chemistry language, it's referred to as fusion, which seems kind of weird as to why we would call turning from a solid into a liquid fusion. We don't normally think of fusion as, we think of fusion as being solidifying something, right? But that's not the way it is. In chemistry, melting or fusion is changing from a liquid to a solid to a liquid. If we go in the opposite direction, a liquid to a solid, we end up with freezing. Okay, liquids to gases, we refer to that as vaporization. Evaporation and boiling are two different versions of vaporization. Condensation is the opposite, going from a gas to a liquid, as if we get condensation on the outside of a glass. Last kinds of changes are under certain pressure conditions. Some chemicals will go directly from gas to solid and skip the liquid phase. We refer to that as deposition. And if we go in the opposite direction, going from a solid straight to a gas, we get sublimation. Okay, you'll notice that each of these has an energy change related to it. As we go toward gases, we have endothermic processes because we have to add energy to the system to go in this direction. And likewise, if we are going from toward solid, we are getting energy out of the system. And so as we do, for those are exothermic processes as we come down. Let's go ahead and take another quick video showing these phase changes at the particle level so we can envision them that way.
Molecular Simulation of Water Phase Change by Mike Daniel of Bakersfield College. Simulation by PHET Interactive Simulations, University of Colorado, phet.colorado.edu. This molecular simulation shows how the macroscopic properties of water change as we increase the heat energy added to the water molecules. Atoms are displayed as balls, and atoms bonded together in a molecule are shown in contact with each other. Water at minus 116 Celsius is well below its freezing point of 0 Celsius. Each water molecule is shown as a red oxygen atom with two small white hydrogen atoms connected with two strong polar covalent bonds. Each molecule has two hydrogen atoms bonded to a red oxygen atom in a bent molecular shape. We see many water molecules very closely packed together, moving in place, but not moving away from the nearest neighbors. Between different water molecules, the hydrogen in one molecule is close to an oxygen atom in a different water molecule. There are some open spaces in this collection of molecules. This is solid water, where it has a definite shape and volume and the molecules are very close together. As we add heat energy by putting a fire under the container, we see the temperature increase and the water molecules moving faster. The molecules are still close together, but they lose the open spaces. The volume is shrunk due to losing the open spaces between molecules. Some molecules can now move away from neighbors, and a few leave the group and move up into the container. The temperature is between the melting point of 0 Celsius and the boiling point of 100 Celsius. At this temperature, the solid water has melted to make liquid water, and some molecules have enough energy to escape into the vapor or gas phase. Raising the temperature to well above 100 C, the boiling point of water, the molecules are no longer close together. Molecules move in straight lines until they hit another molecule or collide with the container walls. Now the volume and shape of the gaseous water is the same as the container. The liquid water has boiled. This entire heating process can be reversed by taking heat energy away, condensing the gaseous water into liquid water, and freezing the liquid into solid water. To see more science and math simulations, go to phet.colorado.edu.
So when we talk about changing state or changing phase, there are two related energy considerations that we need to make. So we've talked sort of about what the particles are doing and how that works. But in terms of energy, we need to think about two things. What energy is needed to change the temperature? And then what energy is needed to change the state? Okay? So let's start with the first of those, the energy needed to change the temperature of a substance. This is related to a energy or a thermodynamic property that we refer to as heat capacity. Heat capacity is the amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. Okay, different substances, depending upon what they are, have a different specific heat property. Okay, so depending upon what the substance is, it may heat up more quickly or may heat up more slowly, or in other words, with more or less energy being added to it. Now, heat capacity does not depend upon the amount of substance that we have. It's independent of the amount of substance. In order to incorporate the amount of substance that we have in, we refer to it as specific heat, because this is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. Okay, and the way we calculate specific heat is we calculate what was the heat transferred, the number of joules, divided by the mass of the substance and the associated temperature change. Okay, so the specific heat, again, C of S, specific, is the heat transferred, Q, the mass of the substance, M, delta T, the temperature change. If we rearrange this, we can end up with this equation of Q equals M times C times delta T, or MCAT, as we like to remember it, right? And that is also the change in enthalpy of a temperature change. Okay, so the Q is the delta H, as long as this is a constant pressure process. So this is the equation that we are going to use in general for us to be able to figure out the amount of energy that's required to change the temperature of a substance. Okay, one last note here. C, the specific heat of something, is typically registered for us in joules per gram Kelvin. Okay, this is going to become important that this is in joules because as we see in the next energy considerations, the changing temperature, that unit's going to be a little different. And so when we get to calculations later on, we want to recognize that we need unit consistency here. All right, so then that was the energy to change the temperature of a substance. Okay, there's also an energy required to actually go ahead and change the phase or change the state. This is the energy either required to separate IMFs or bonds, or the energy that is released when bonds or IMFs are formed. Okay. The heat of fusion, remember fusion is melting, okay? This is the energy required to change a mole of solid at its melting point to a liquid. Okay. Heat of vaporization, okay? This is the energy required to change liquid into gas. It is equal to the heat of condensation, the reverse process. And last but not least, heat of sublimation. It is defined as the energy required to change a mole of solid directly to a gas. It is equal to the heat of deposition. When we see these heats recorded, you'll notice that the units of these are kilojoules per mole. So in order to figure out the actual heat, we just need to figure out how many moles we have and recognize that the units of this are in kilojoules. Well, because oftentimes we'll be asked to calculate the amount of energy that it requires to take a substance through a series of temperature changes and phase changes. And if we map that out, what we see is something called a heating curve. Okay, so what basically happens here is if here's my substance, they tell me ice, right? And I start with that at a temperature of negative 25 degrees Celsius. What we see is that as we start adding energy to that, the temperature rises and rises and rises, and it rises until I get to that melting point, okay? And once I get to that melting point, the temperature, the heat added to the system is no longer used to go ahead and make the particles move faster. Now the energy goes into pulling the molecules further and further apart from one another. All right, so if we do that, the melting point and boiling point are going to depend upon the IMFs and the bonds, whatever temperature those are at. But the temperature of the substance does not rise during that phase change. Okay, so we're going to go ahead here and we're going to go ahead and add energy until it is all melted. Once it's all melted, we're going to go ahead and we are going to increase the temperature again of the liquid all the way until we get to the boiling point. And at the boiling point, once again, all of the energy goes into changing the material from a liquid to a gas. And once it's all turned into a gas, then we get a temperature change again. Okay, so energies associated with this are additive as we move through. So again, right here, in this particular case, we are heating the ice up. So in this particular case, we would be using Q equals mc delta T, where C being the energy required to increase temperature, which again is going to be the specific heat of ice. Then we get to this section of the curve between B and C. Okay, that is where melting is happening. So in this particular case, we are going to go ahead and we are going to use the heat of fusion of ice, or H2O. Okay. Then once we get to section C through D, again, temperature is rising, so we'll once again use Q equals MCAT. This time the specific heat is going to be the heat of water, okay, liquid water. And then we get to D through E, where we are where we are boiling this thing. So that's going to be using the heat of vaporization for H2O. And last but not least, once it's all vaporized and in that form, we're going to once again use Q equals mc delta T, except for this time the C of S is going to be for steam. Okay. All right. So then the energies are additive. So if I wanted to get from one place on this curve to another place on this curve, I would just figure out what are all those segments of energy that I need to add up in order to make that happen.